Good morning, good afternoon, and good evening, and welcome to the Friday talk show of Global Electronics with your host, Rajiv Kulkarni. Today's date is June 20th, 2025, and it's 9 a.m. Central Standard Time of USA, as I live in Dallas, Texas. So, Global Electronics' main objective is to bring different subjects on electronics manufacturing, whether it's design related, whether it's manufacturing process related, or quality or market or the trend in the electronics market that is happening globally. So good morning, good afternoon, good evening, because we don't know which part of the world you're watching this show. And every week we try to bring a new topic. The speakers or the guest may be same people sometimes. And one of our very esteemed guest, as you have seen, Mr. Ambaprasad has been contributing with us a lot in the electronics side of it, because with his wealth of experience in the industry for the last 4+ decades, we are bringing the best possible topic that is catering to the electronics design aspect, I would say, and which is not only design. When it is design means it's also related to the manufacturing activities. So what is the topic we are talking about today? It is a continuation of why is the V model important for Ultra HDI PCB design. So we call it as 2.0. So there's one more episode of the same subject which will happen next week. That would be called as 3.0. But today's thing is designing Ultra HDI PCBs present significant challenges due to their complexity. Yes. So the complexity of circuits have gone up. Why I say that is, as we all know, the electronic circuits are becoming more and more dense as the requirement of smart electronics is increasing day by day, whether it is consumer electronics, home automation, or we talk about aerospace, we talk about transportation, we talk about rail system or electric vehicles, or we talk about the automotive infotainment system. So because of that, the complexity of the design is growing and growing on the upward side. And for that, we are addressing these kind of challenges and these kind of issues that are being faced. So let's welcome the industry expert, the technology expert, and the design expert, Mr. Ambaprasad, who lives in the Silicon Valley of India, which is called Bangalore. And he has been in the industry for more than 4 decades in the design sector, and that too on the printed circuit boards. Welcome to the show, Mr. Ambaprasad. Good evening. How are you this evening?
Yeah, doing good.
Excellent, excellent. So how is Bangalore weather? Is it raining there today?
Yeah, it rains here and there and now and then. I mean,
Oh, now
same
and then
place,
and here and
different,
there.
both here and there and now and then. It is very unpredictable.
Yes, 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 Ambas. So let's share the screen here. Let's go to the
Yeah.
presentation mode. As we every week we bring in different types of presentation, and Mr. Amba Prasad puts it very meticulously. And so let's get on to the straight subject, and let's continue, Amba Prasad. So exactly, let's, if somebody has missed last week's show. So what is V model? If you can briefly first mention that, then you can start, about the subject.
So V model is generally used in program development, software program development. On the left arm of V, you put the requirements and implementation at the bottom of V. And on the right arm, the subsequent testing and validation, whatever you have to do, for every action here, there should be a validation on the right arm. We just put there so that we know what to test and when to test. That's a roughly I put a little color coded. Requirements is on the requirement engineering part of it is on the left side, and actual system design and development is on the bottom. That is actual implementation in CAD what we do, and then the verification and validation is on the right arm. And here I have shown just an indicative comparison. Whenever we do PCB layout, we talk of trace width and trace spacing. Okay, some people call conductor width and conductor spacing. There are some historical reasons why some people still stick to earlier methodologies and some people are the leading edge. Let's not discuss about that. But in US and Europe still, it is 75 by 75 micron minimum, and going towards 25 by 25 micron. That is the space and trace width. 25 micron is okay. And then in Asia, especially Taiwan, Korea, they have gone for advanced IC like structures on a, say, redistribution layers of ultra high density. They are 8 micron and 8 micron. Almost you can say it is one third of what the top one is projecting about. Then if there is a LQDX LMI, it is a brand by itself, becoming very popular. And it is about, again, half of what we have shown. It is 5 micron by 5 micron and going towards 1 micron. They're going, but this is mostly on the semiconductor side. So these are the, but when we call Ultra HDI, we are in the middle range. That is 8 micron by 8 micron. 8 micron trace width and 8 micron spacing.
Spacing. Okay. Yeah. Excellent. Excellent. Okay. So let's jump on to the today's topic then.
Yeah.
Okay. So I'll go to the next slide here.
So this is a picturization of this we have covered even when we talked about high-speed design. But let's say why people are going for densification. Densification is okay to pack as much electronics in a small form factor as possible. But even space permitting, when the speed increases, the trace length has got a limitation. The physical length has got a limitation. Even if the space is available, we have to pack them very tight. Otherwise, it won't work. Okay, there are two motivations here. One is to pack as much as possible in a small form factor, or to achieve higher speeds, you have to keep it as short as possible. For example, on the left side, we have density and energy efficiency, GBPS per millimeter per joule per bit. That is the power rating. And then we have maximum distance in meters. So if you look historically, it was within the package, it is 0.00001 meters. Then it is 0.001 meter and 0.01 meter. It is reducing even within the package size is reducing actually. Okay, that is the densification at the package level as the speed increases. Then the interconnect distance in meters within the PCB or in a package breakout region, it is 0.1 meter. But when we talk of a data center or AI, which are the hot subjects today, the interconnection will be through a backplane or a cable backplane, as the people call it. It is 1 meter, 10 meters, and 100 meters. In a campus interconnect, there can be 100 meter worth of cabling can be there. So this is the scenario. This is within package, on board, and off board.
Interesting. Very interesting.
Next slide, please. Yeah. Here we are articulating in a very detailed cross section. Okay, now we have on the upper picture, we have a silicon die, and then we have a substrate or a redistribution layer, and that is where the package starts, and then we can see the bump in between, then it sits on the PCB. A signal is starting from the extreme row, and it goes inside through the bump, it goes to the PCB. Then there are vias and there are trace length. Then again it goes to an optical module. But now, whenever a signal is transitioning from one level to next level, say from die to RDL and RTL to the bump and bump to fan out via in the PCB, and again the journey is back. It travels a certain distance and comes back to the optical module through another via. See here, every via and every bump introduces a loss and introduces a reflection due to impedance mismatch. So here we are telling, again we are talking of ASIC through substrate, PCB traces, length losses, copper loss and dielectric loss. Then via losses, all vias are lossy. They cannot be a lossless via. Okay, they are simulated. Then 53 Gbps, 106 Gbps, 212 Gbps. And people in the data centers, they have gone up to 440 Gbps and onwards and all. They are just going. These are the losses. So what it means is each interface in the link between ASIC to optics adds loss, which requires additional power to overcome. Okay, we may put a buffer or a retimer, but these retimers and buffers will, they add the strength, they can drive the distance for a longer distance, but they consume power. So system becomes hot. The losses grow, just 1 minute. Previous. The losses grow with each generation of interface speed. Okay, now let's say I'm having 112 Gbps, same package, same PCB, same optics. If I want to drive to 224 Gbps, loss can be even, I have to reduce everything, the distance by 1/3 at least, even keeping something in the buffer.
Okay. Interesting.
Next slide, please.
Yeah.
So how the package designers are overcoming the problem? So the favorite topic again, 40 years back or 30 years back, we are going. I mean, we cannot stop pedaling backwards. I mean, that's the problem. Conventional packages, BGA, 1990s, supposed to be very, state of the art at that time. That is a 2D integration. BGA was a 2D integration, X and Y. Then became 2.5D. They started putting more substrates. This is still conventional. Then horizontal integration. You went for 2.5D multi-chip module, a fan-out multi-chip module. Then it became 3D. In 3D, they use through silicon via and they start integrating vertically. You can see somewhere we have written vertical. You can see something like a multi-stored structure. Okay, this is something like, you build a huge bungalow or you build more floors on the same floor space, same area. It is like that.
Same area.
3D is vertical integration. Now, the latest is the optical part and the electrical part are getting combined in one package, which is called as a co-package optics. So why I have taken co-package optics as an example, here I can show the Ultra HDI implementation. This is one of the examples. Ultra HDI can happen in all other sectors. It can happen in so many other fields, but co-package optics brings its own challenges because optics, they still use I show you some trace widths earlier, which are still wider traces. They use still wider traces over there, and they want to combine that with a very narrow traces also in the electrical part. But in the optics part, they still use old nanometers. So that's the idea. That's why I thought co-package optics is a very good example to explain in detail.
Absolutely.
Whatever I have shown like a staircase in the previous, here I am showing in a graph. You have a logic and memory in a PCB. Generally, all memory modules are kept as close to the CPU or GPU as close as possible. So 1D packaging, then a 2D packaging, then we are having 2.5D at the chip level and 3D at the chip level. This is how the packages themselves, when we say very lightly, packages are behaving like PCBs and PCBs are behaving like packages. That's what we say. If you look at the 3D chip level, it also looks like a multi-layer structure.
Multi-layer structure, that is
Yeah.
correct, yeah.
Yeah, photonics and CMOS, we are putting in the same core package optics. The challenges are verification and sign off. At every level, we have to sign off. We schematic, you sign off, you do placement, then after placement, you sign off for routing and signal integrity, power integrity, etc. LVS, that is layout versus schematic, thermal and mechanical compatibility, design rule check. Then in CMOS, but in our photonics, it is optical sign off. Then RDL, fan out routing, laser assembly and bonding. Thermal mechanical analog EM RF simulation power, a multi-physics simulation. Optical interposer loss, fiber attach, fiber loss, laser bonding, electrical optical co-simulation. This is a very good example where our V model can really apply. Most of these things will be on the left side of V. Then
And in fact,
interposer physical design,
yeah,
physical design, and
in fact,
yeah.
there is a question saying that
Mm.
how does the V model ensure quality and reliability in PCB design? So, yeah.
Yeah, I'm just evolving towards that. Then I'll come to that. Maybe today we cover or we may cover in the next session. Question
Okay,
is
okay,
understood very well.
okay.
It's a very right time to ask the question. And this question will be answered, no problem.
Okay,
So high
okay,
level
okay.
pathfinding. So pathfinding means, for example, the package bump pitch or a package breakout region can be planned for 224 Gbps sort of an operation, but still we can put 112 Gbps over there so that they can be reverse compatibility. So that is pathfinding.
Hmm.
Next slide, please. Uh, these are the design trends. Element and 2023 state of the art, and by 2030 where we are going to be. But the way things are happening, even yesterday I was in a road mapping meeting which we are going to rewrite the road mapping, a light revision. Whatever we may project as 2030 can happen as early as 2028 or 2027, provide the way how the AI market is picking up. So most likely what we say as 2030 can happen in 2027 itself. Power, current density, efficiency, 600 watt may go up to 2000 watt. Die IO density, 10K per millimeter square can become 20 million per millimeter square.
Sure.
Unless we go for a 3D packaging, we cannot achieve that. Okay. Then die bandwidth 30 Tbps, 500 Tbps, and this will happen only in data centers. This won't come into the even a server platform. It will happen in data center AI application backend. So let me tell the audience what I mean by AI backend. Even today, the 30% of the server market and 30% of data center market is dominated by four key players. They are whatever they are designing, they're using for themselves. They're not selling in the market. Okay. There are very big names in the industry. In fact, one of them is a number one in the industry. Of course, we unnecessarily we don't take a brand name over here, but people can understand who are following this program. So then
Yes.
capacitance, silicon interposer, so many things we have mentioned. So
Correct.
so that's how it goes. So almost it's not even tenfold. Sometimes it can be 20-fold increase in density. This is only possible if we go through ultra high density.
Yeah.
Maybe you can take a break now.
Yeah, I'm going to take a break. I was about to say that. Then we'll come back just after this break. I'm going to stop the sharing the screen and run this 30, 50 seconds our Good morning, good afternoon, and good evening, and welcome to the Friday talk show on global electronics with your host, Rajiv Kulkarni. Yes, every Friday we bring you this 30 to 45 minutes talk show on various topics in the electronics manufacturing sector. And today's topic is V model and its importance in ultra PCB high definition, high density PCB design, that is 2.0. Last week we had the first session on this, and today we are going to have the second one, which is 2.0, and the next one we'll have the 3.0. So we have Mr. Ambaprasad, who is an industry expert, PCB design expert, and been in the industry for the last 4 decades. And he lives in Silicon Valley of India, that's Bangalore city in Karnataka state in India. Welcome back, Ambaprasad, after this small break. And let's continue our discussion on this V model and its importance in the electronics industry. Yes, sir.
And next slide. Yep. So the Ultra HDI is not only used in PCBs, it can be used in redistribution layers also. Uh, Again, here I have shown some of the how the trace widths and spacings and bump pitch have evolved from 2018 up to say right now we are in 2025, we are already in 2034. So when we say 2025, the design might have happened in 2022 or something, that people should read that way. I cannot design yesterday and sell tomorrow. Okay, that people should realize there can be some lag in what we are showing. So what we are telling in, that's what I told you, when we say 2034 deployment, it can be 2030 implementation at the CAD level and so on. And maybe 2 years, we may have the design will start at least 1.5 to 2 years earlier. So FCBGA line width and space in microns was bump pitch was 40 mil, 80 mil, 130 mil, 100 microns, sorry, not mils, microns. 40, 80, that's what we are evolving towards. And it may still stop at around 90, because the packages you want to have the same old packages bump pitch to be used using a redistribution layer, it fans out into the die. So that's still there. And I think the 90, 80 are somewhere around 90 to 100 microns will remain for a long time to come. Otherwise,
Wow.
same packages are used in a regular PCB also. So that's why it stops there. So that we should know. And then micro via diameter, 50 microns, 50 microns, 40 microns, going towards 30, 30, and again, it remains same vicinity. 30 to 20 is not a big jump, because even if you try to reduce, you will not get much results out of it. So people may have to invest a lot of time, money, energy in achieving a result which they may have to spend double the time, triple the money to achieve 1.1 results. That's why they stop at that actually. They want to extract benefit out of the previous bump pitch or whatever. Chiplet is where we, actually these were known as MCMs earlier in the 90s, but now they are called as chiplets. IEEE changed the name. Chiplet, a chip, it means a bigger chip. Chiplet means baby chips. I mean,
Baby
chiplet.
chips, yeah.
Okay.
Yeah.
Okay. Like that, fan out organic interposer. So again, 2 micron by 2 micron, 2 micron by 2 micron, which may go towards 1.5 or 1 micron or whatever it is. But what they are showing in the red color is a bleeding edge. It may work or it may not work. Okay.
It may not work.
Then micro via diameter, 30 microns, 20. Again, going towards 10 and remaining at 10 and 5. More or less, it is the same. And then chiplet 2.5D, 3D. Okay. When we say organic laminate, that can be a PCB also, Ultra HDI PCB, or it can be redistribution layer also. But when you go to the silicon, Yeah, silicon, they have got their own stuff. That's a different stage altogether. 0.6 by 0.6 micron. They're still, again, they are still at 0.6. They don't want to invest further on that, at least for the chips which are going to be used in a regular market. Okay, next slide, please. So challenges in implementation, what we are showing as a cross-section is just a diagram. It may not be a working model. So let's warn the audience. It is just a intentional diagram, how it looks like. Okay. Motivation, high speed. Approach is high speed IO on substrate. Then challenges, signal loss, electrical loss, and the body size. Body size correlates to length, what I was telling earlier. We cannot have infinite length or a width. So that is the challenges. A large capacity for data processing, multi-core on a die, large die, yield and manufacturing cost. Complex assembly, chiplet, power delivery is an issue, large body size. Power delivery, in fact, people have devised what is called as a backside entry, a power entry for larger chips. That can be a separate subject altogether, maybe somewhere in, say, November or December. Let's wait for that. Then low power consumption, this is always the true. Then narrow pitch, bump pitch scaling. And pitch scaling will happen according to JEDEC standards. We cannot do, either we are compatible to standard or we are not compatible to standard. Okay. Okay, then yeah, high density circuit. So everything is pointing towards ultra high density. Next page, please. Same diagram. Challenges in semiconductors. So previous one was in Ultra HDI, either a redistribution layer or a PCB, but here within the silicon. And of course, if we do heterogeneous or a CPO or something, we have to mix and match. So large body size, high density circuit, electrical property, power delivery, low warpage, and the packages become wider and wider. There is a warpage issue. Narrow pitch, bump pitch, signal integration, more efficiency in power delivery, warpage control, sinkage control. People have their own simulation and methodologies how to control this. Fine space fabrication, narrow pitch through hole. When we say through hole, read it as a through silicon via. Then pattern and package design. Now everything is additive process. It's not structured. Embedded multi-layer core. That also can be a separate. I'm going to show after a couple of slides how it looks like. Then mechanical properties. Coefficient of thermal expansion should be low because there are such a multi-layer structure. They start expanding or contracting in a different way. It may crack the vias. So it is to be very low CTE. High drill processability. Drilling should be very easy. Even when we say lesser drilling, it has to be very easy. Low decay and DF. Almost decay and decay of vacuum is 1. And as close it goes towards that, it is good. Signal propagation will be faster, but the state of the art is almost around 2 to 2.2. Then super flat rate, high resin flow prepreg. The PCB technologies are coming into Ultra HDI. Okay. This is the thing. So that's what I told you sometime back. PCBs are getting into packages. Packages are getting into PCBs.
PCB. Yeah.
Next slide, please.
Okay. So I think we are almost.
Light motif of a core package optics. Light motif means, let's say you make a music. You repeat the same music again and again and again. If you see Star Wars movie, for example, whenever Darth Vader comes, you hear the same music and again and again and again. The same composition gives a very good result. So even if a person is sleeping in the theater, when the music plays, Darth Vader is coming, he will wake up. So this is the way. So when we do packaging or whatever, certain things will repeat. Certain things are characteristic to that. So that's what we are showing. A comprehensive structures for heterogeneous integration. Now when we say heterogeneous integration, this is nothing but multi-chip modules and chiplets. Okay. Heterogeneous integration, ultra high density fine pitch lead and spacing and bonding. complex interconnection and combination of platform structure. Now, our optical may get into this. Actually, it is there. You can see a cable hanging at the edge just as a schematic. Then from a wafer, you go for a panel and you go for a package. Then you can see the bumps which are going to next level and to next level. You can see encapsulation in blue color. That encapsulation is put so that there is no contamination or it will dampen the CT mismatch. So that's another material coming into picture. Then in the PCB, you can see the vias, blind and buried vias, micro vias, and also there can be embedded components over there. And then we can see the actual bumps or balls which interact with the PCB at the bottom in gray color. So that's how this is actual package. It can be placed on a PCB or on a socket. Advanced
Excellent.
metrology, inspection and analysis, electrical thermal stress reliability, material chemical characterization and simulation, then non-destructive inspection,
Excellent.
metal composition, electromechanical surface and morphology, even this EM migration we covered sometime earlier. So that plays an
Yes.
important role. All this will come on the left side of the V curve. Okay.
Okay. So
In-process
that is
inspection and critical measurement, electrical and optical interconnection, 2D and 3D defect detection and measurement, multi-sensing and full automation in smart manufacturing, ML and AI-assisted inspection and integrated diagnostics. This is where AI comes into picture. Your AI has got the failure modes, pictures taken, there is an album, there is a gallery is available. When even if it is not aligned properly, it will not go to the next step so that we don't waste packaging. And the beauty is you require this technology to make AI work, and you require AI to make this assembly work. So this is a closed
okay.
loop. Okay. So this will
It's
come on left side of V curve only. I think we can stop at that. And maybe
okay.
next time I will tell what comes on the left arm of the V and what comes in the bottom of the V and what comes on the right side of the V. And maybe another half a session to cover. Don't take V model has got its own limitations. So we also tell people what are the limitations. Yeah.
Excellent. Excellent. So, of course, the question which was earlier asked about the how does the V model ensure quality and reliability, that we will answer in the next session.
Next week,
And
yes.
also there is a question showing asking uh, how it is applied in PCB design. So I think you went through certain slides, probably definitely
Yeah,
that
yeah.
would
Maybe we can
explain.
explain next time. Yes.
Yeah, so that is, and also it is explained. People, you can watch this show after our live show is done, and you can still click the link and you can watch the recorded version, and you will know that, and you can go back also on the previous thing. And of course, we will also talk about the benefits of using the V model in the PCB design in the next session. I would say it would be the concluding session of V model in the HDI PCB design, and how it is compared in other design methodologies. I mean, V model and also the other design methodologies, the comparison, probably people want to know. So these are some of the questions which we will make sure that we will get back to you in the next session. So, Mr. Ambaprasad, any messages before we say bye for today's talk show?
There is no message, but still, though we run madly behind state of the art and the bleeding edge, still the old technologies work. Even in server boards, there are certain regions where a conventional PCB design works, especially in the power supply region. Don't forget them. I mean, it is nice to learn new things, but don't forget whatever we have learned so far. So that still
Yes.
works. It's a combination of both. We have to uh, have both the bleeding edge as well as the conventional, then only it works. Because whatever we have invested in educating people uh, and learning, even we educate CAD. I mean, the CAD also gets educated by us actually. So whatever
Yes.
we say, the CAD companies will implement and give. So these things we should not forget. So that's number one. Number two is also I would like to add one or two slides to show where the task force or the staff should know how much assemblers should know design and how much designers should know about assembly. Is not totally, there is no, it is not watertight, but people should know certain things. Otherwise, every person will be looking at at their own perspective, and there will be a lot of you know uh, arguments and counter arguments. But that is how it works. That is the beauty.
Yeah,
And
that
I
is true.
always like critics and skepters. In fact, when we worked in 90s, there used to be a DFM package called as a skepter. It
Yeah.
is skeptic. Always it doubts. You do when you say what is 1 plus 1, he will say 1.9 to 2.1. That is the answer he used to give. So this always happens. So nice. Thanks for your time and the audience time. So maybe we
Thank you
can
very much.
again touch base next week.
Next week. Yeah. Thank you very much, Mr. Ambaprasad, for your valuable time and valuable wealth of knowledge that you share with our audience. Audience, if you are not watched today, if you couldn't watch, you can watch it, the recorded version. And when we share that again with all you all. And thank you so much. And wherever you are, whichever part of the world you are, please take care of yourself and God bless and have a wonderful weekend. Thank you all.
Wow.